is what here's what we were talking about last. Well, it's what we've been talking about for the last few days. Let me say that. Integrals, and just so we spent a little bit of time as a reminder talking about single variable integrals. Let's not forget the big point: single variable Okay, and I'm sorry, my computer is acting weird now. Okay, all I have to do is close this and open it again, and it should be fine. Okay. Why am I? Okay. Sorry for the delay. Okay. So, the big point. Single variable integrals are Riemann sums. In general, integrals are Riemann sums for the purposes of this course. And so, again, if you have this kind of mental image in your mind, if you like to think about integrals as being area under a curve, it's relatively harmless, but it's not 100% harmless. There's going to be situations where that's actually counterproductive, right? So I want to encourage you to, try to really embrace this idea that integrals are Riemann sums. And we've seen some I'll get to the applications in a minute. So a quick reminder, this expression here has these four properties, right? But if you write the four properties this way, note it doesn't actually say one-dimensional domain anywhere, right? So we can try to retain these four properties while applying, those ideas to a two-dimensional domain. Right? So here's where we were. We talked about this again. It was a few days ago at this point. And chopping up a two-dimensional region instead of a one-dimensional interval into little pieces of area, not length, right? And doing the same kind of a Riemann sum gives us this expression. And this is called a double integral. Okay. All right. So strategically, again, here's the idea. Applications can be written as Riemann sums. Lots of applications that we talked about, and I'll quickly mention again. That's why we make Riemann sums the definition of a double integral. And so it is double integrals, aka Riemann sums, that we want to find a way to compute. Volume under a graph? I know sometimes, maybe, but that's not the point. It's Riemann sums that we really care about, yeah.
Why is that not written like a nested Riemann sum?
Well, that's because that's a subsequent realization that we're going to make later. But I'm going to come back and talk about that in a couple minutes. Let me defer your question, if I may. Yeah. Okay. So we will come back to that. Okay. So how do you compute? Well, so we go to the volume under a graph, and we make the realization that you can. I'm sorry. I got ahead of myself. Here's some applications of double integrals. Volume under a graph is one. Mass of a sheet. Population. All right. Anytime you know stuff per unit size, in any sense, you can multiply by size to get stuff, and stuff adds up. Right? Okay. All right. Okay. So how do we compute these double integrals? And I make this argument about volume, and it's I phrase this as the geometry problem. This geometry application, but ultimately, though, the big punchline is that if we can compute volume with these nested integrals, and if we already knew that we could compute volume with double integrals, this is a strong plausibility argument that you can use nested integrals, iterated integrals, to compute double integrals. I claim this is what we're ultimately going to care about, because, again, that's what connects to applications. Not so much that, right? This is what connects to applications. Okay. All right. So here was a one application when we compute the mass of a sheet. So we've been through this example already, so I'll go quickly. Mass is a double integral. It's mass per unit area times area gives you little pieces of mass, and you add up all the little pieces of mass, right? So highly plausible argument. So that's step one. Step two, I rewrite the double integral as an iterated integral, because we can. And then step three, why do we like iterated integrals? Well, iterated integrals I like because I can evaluate iterated integrals inside out. You got to start on the inside, or your integrands. and ultimately then compute the answer to the whole question. Okay. Now to get back to your question, so why do we need double integrals? Is ultimately, so what I think is going to address your question. So let's suppose that I were to say, come back up here and say, well, look, I can compute volume with an iterated integral. Why don't I just scrap this whole idea of a double integral that I had in the first place? Why don't I reject that as ultimately inefficient and just never look back? Right? And here's the idea. If I were to try that on this question, it would crash and burn. If I were to skip this right here, let's say, forget about double integrals, who needs them? Right? And try to immediately connect this mass question to an iterated integral. How do I even get started on that? I would have to make the observation, starting with the outside integral, I would need to try to make the case that somehow this thing is something that you can multiply by length to get mass. The accumulating, as it adds up over this interval from 1 to 3. So, but don't forget, in this problem, we're talking about mass per unit area. That's all I know is mass per unit area. Mass is distributed area-wise. I have a formula for mass per unit area. What is it that I would multiply by length to get mass? Well, that'd have to be mass per unit length. I don't know what mass per unit length is. That doesn't even make sense, really. Let's go to the population example. I can talk about population per unit area. That makes sense. You give me an area. I can talk about how much population lives on that area. What is population per unit length? I don't know what that is. Right? So it doesn't really make any sense. The interpretation I like to make of this is that this particular application, one sort of nice thing about the graph application, the volume under the graph, is that because it's 100% geometric, we have these kind of intermediate notions. The intermediate notion that was lacking in those previous example, intermediate notion to volume, is area. We have geometric experience and geometric intuition that allows us to be comfortable with this idea of area, right? Even though the question was about volume. Right? That still kind of makes sense, but that's a peculiarity of the heavily geometric nature of that one application. Okay, if you're doing anything other than computing the volume under a graph, in other words, most of the time, right, you've got to have this idea of a double integral so that you can take ideas like, mass per unit area and multiply them by area to get the mass that you're actually interested in. Okay, so double integrals still necessary to connect to the applications. Where's my button? There it is. Okay. All right. So this is kind of an unavoidable strategic flow chart of how you're going to solve these kinds of problems. We've got to have double integrals because applications connect to double integrals. Right? So that's step one, is to take your application and rewrite it as a double integral. Step two, let's recognize we don't have a fundamental theorem of calculus for double integrals. Wouldn't that be nice? But we don't have such a thing. So we can't just immediately start evaluating. Step two, I have to turn that double integral into an iterated integral. Nested integral, if you prefer. And having done that, then I can apply the fundamental theorem of calculus 2 times, and get an answer. Okay, so this is the flow of problems. I tend to refer to these as phase 1, phase 2, and phase 3 of an integral application. They are different kinds of steps. Very often we're going to find ourselves interested in this part, and how do you compute the following iterated integral? I mean, there's techniques there. You have to think about, well, wait a second, what's constant at what stage of the calculation? Do you remember all of your single variable calculus, rules for how to do integrals, that kind of thing? What we're going to be focusing on a lot today is this part. Given a double integral, how do I turn it into an iterated integral? Right? If the domain is not a rectangle, that's non-trivial. Right? So that's sometimes the focus of the problem. Today, when we're talking about this, let's not worry so much about, what's the application. I don't really, it doesn't matter. We've got a double integral. There's some application that's given us a double integral. Let's just take the double integral. Let's focus on how to turn the double integral into an iterated integral. Likewise, at the end, let's not crank out and actually get a numerical answer. That's also part of the problem, but it's not what I want to focus on. So today, or at least a lot of what we're going to do today, is focus on this one sort of phase of the problem. Okay, so now again, we're still in stuff that was on the recording, but again, I wanted to kind of hit some highlights. What if your domain is not a rectangle? And the argument that we made is that everything pretty much goes through. Not that much is different. The only difference really is that this inside integral, right, is going to have a starting bound and an ending bound that depend on where you are, right? So for that value of x, we get, certain y1 and y2, but you can see if x moves over, as x moves over, these points are going to move, this one's going to move up, right? This one here is going to move up and then down. So those bounds are going to change depending on x. So they are functions of x. That's the big punchline, is if your domain's not a rectangle, then the inside bounds are functions of the outside variable. And it's just, kind of a nice little punchline. Specifically notice they're functions of the outside variable. Okay. All right, a little bit of terminology. I like to refer to this integral here as the inside integral, and I like to refer to this integral here as the outside integral. There's a temptation to call them first and second, and this is ambiguous. Depends on what stage of the calculation. You'll probably notice that as you go through the slicing process, you slice outside in. But then when you evaluate, you have to evaluate inside out. So when you're doing your slicing process, the one I've got colored up here, the dx integral is the first integral in the slicing process. But the dy integral is the first integral in the evaluation process. So anyway, just to avoid that ambiguity, try not to say the first integral, the second integral. Let's say inside and outside. I think it's nicer. Okay, so there's an example that we went through. I'm going to let that stand. I think that should be fine. We've got a bunch more examples to come, so I think that'll be good enough. Here was a sort of a multi-phase example. Step 1, phase 1, turn the application into a double integral, and then we addressed phase 2 of how do I turn the double integral into an iterated integral. And then we address phase 3 of how do I turn an iterated integral into an answer. Okay. All right. Okay. Another couple of phase 2s. And given this domain, how would you write a double integral over this domain as an iterated integral? We talked about the details of this. Note you can slice in either direction. Your choice to which way you want to go. If you want to do your dx slicing, because I said slicing, I think it's reasonable to say first. Right? It's first in the slicing process. Then dx goes on the outside. On the other hand, if you want to slice with your y slices first, then dy is on the outside. Everybody on board? Everybody comfortable with all this stuff? Good. Okay, so that's where we were at the end of the recording. Let's go on from there. Here's another example. Lots of examples coming up here. This is a phase 2 problem. Let's not worry about where this double integral came from. We're computing something, right? Some application. Here's my double integral. Let's worry about how to turn this double integral into an iterated integral. Okay, the domain is this region right here. I want to make a quick comment about language. You're going to see this language a lot. This domain is bounded by a couple of particular curves. So bounded by means a couple of things. Let's draw these curves, by the way, first. This curve is that. This curve is that. We have this purple curve. We have this red curve. Okay, the language bounded by means two things. It means that these curves make up the boundary of the region that I'm talking about, but it also means that this region is actually bounded. It means that it doesn't run off to infinity in any direction. You can put a fence around this region. Okay, so for example, I mean, you might say, you take away that last requirement, you might say, well, hey, this region over here, that region, its boundary is, well, it's made up of the purple curve and the red curve, but it's not bounded. Right? So these two curves break up R2 into several different regions, but only one of those regions is actually bounded by those curves. Is everybody clear on the terminology there? So there's in some sense, every time you see one of these problems phrased in this way, there's unavoidably a geometric interpretation problem. That's part of the problem. Right? It's part of the question is to figure out what region is being talked about. Okay. Alrighty. So that being our region, let's think about the slicing process. Now I'm going to do this slicing process with my X slicing first. By the way, keep in mind terminology. When I say X slicing, what I mean is we're going to look at slices that represent a constant value of X, which means, and you might find this a little awkward, that we're taking slices perpendicular to the X-axis. Some people want to label it the other way and say that, an X slice should be parallel to the X-axis. This doesn't make any sense, really. The point is that these slices, this slicing process creates the dx integral. So it really, really makes sense to call these X slices, and therefore, unavoidably, the slices are perpendicular to the axis. So heads up, that's how the terminology is going to go. That said, here's our X slices. Our X slices start, let's see, at that point. Right? Let's go through the game. That point is on these curves. These curves have these equations, and if you take these equations and go through and do the algebra and solve, you get -2. Right? Everybody remember that process? Bounds are determined by points in the domain. Points are determined by curves. Curves have equations. Equations allow you to solve for what you're interested in. So always sort of think about that progression. Okay. All right, the end point. Well, sorry, getting ahead of myself. The end bound. That bound is determined by that point. That point is determined by these curves. These curves have these same two equations, and again, do the algebra. You get 2. Heads up for thinking about the pluses and minuses. Technically, both of these points are determined by the same two curves. How do you know which is which? Look at the picture. Right? Think about, is it positive or is it negative? It should be clear. Right? Okay. Everybody happy? Am I going too fast? Am I going too slow? No. Just perfect, apparently. Okay. All right. Okay, so now for a given value of x, we're going to fix a value of x somewhere between -2 and 2, and then for that value of x, there's what our y slice looks like. Right? So our y integral, well, let's see here. The lower bound comes from that point. That point is on, just for focus, I'm going to erase these other things. That point is on this curve. This curve has that equation. Solve for what you're interested in. Wait a second, what are we interested in? We're interested in y. So I need to solve for y in that equation. And I get x squared. Again, it's a little uncomfortable. Makes you feel like, well, am I allowed to put a variable as a bound in an integral? Can you do that? Remember, that's not a variable. That is a constant now. right? It's further to the outside. It's the variable for the outside integral. So for as far as this inside integral is concerned, x is a constant. So we have solved for y as a constant. Everybody happy with that? Everyone on board? Okay. All right. Ditto for the top variable, the top bound. That upper bound is determined by that point. That point is on this curve. That curve has that equation. Solve for y. Bam. Okay. All right. Now, why did I do my x slicing first? I don't know. No particular reason. Right? Sometimes it doesn't matter. Here, it doesn't matter. We did it each of two different ways. They're both equally kind of simple. Not clear to me which one of these is preferable. It doesn't matter. Take your pick. Whatever. Not worry about it. But sometimes it does matter. So this is an example where kind of matters a little bit. Not a huge amount, but here's what would happen if we'd sliced the other way. Let's see what would happen if we had done our y slicing first. Right? Slicing perpendicular to the y-axis. Slices look like this. Our bounds... Our lower bound is on this curve. That curve has this equation. Solve for, I'm sorry, I got ahead of myself again. Slow down. Okay, y goes from 0 to 4. Let me just go through that one quickly. Right? So I think that's pretty clear. X, though, is where it gets interesting. The x bound... How do you find your x bounds on a given y slice? Right, x starts here. That point is on that curve. That curve has this equation. Solving for x, and we get a square root. All right. Yeah, everybody see what happened there? Okay. So now, which do you prefer? Likewise for the upper bound. Which do you prefer? Which would you rather deal with as an integral to evaluate? That one or this one? And I guess it's not that big a deal in this case. You could certainly do either one, but all else being equal, I think most of us would rather avoid fractional powers. It's not a super big deal. So how do you avoid this? Right? How can we anticipate this problem and always mysteriously end up with the easy integral to compute? And the answer is just try to pay attention to what is a function of what. So the giveaway here is y equals x squared. And, I suppose you could break this down into two curves, one of which is x is the square root of y, one of which is x is the negative square root of y. I mean, it's not the algebra can't be done, but all else being equal, it's just easier to think of y as a function of x here. Right? And so notice that this choice of slicing is consistent with that. It says I'm going to need to solve for y as a function of x, which is what I would like to do. And if you make the other choice, if you say you're going to slice this way, you're going to need to solve for x as a function of y. And you're going to have to kind of invert a function, sort of. So anyway, that's one way to think about that. All else being equal, take pity yourself. Try to make choices that will make your life as easy as possible algebraically. Here's another example. Here's one slicing. Right, now, in this case, you can make the case that there's three curves here. That's a line. Y equals x. Do I want to think of this as y equals x or x equals y? Who cares? Doesn't matter. Algebraically equally convenient. Here, x equals 2 minus y equals 2 minus x. Who really cares? It doesn't matter, right? Likewise, this is, that's just y equals 0. That's not even worth talking about. But again, it kind of matters in this case which way you slice. It's going to make a significant difference. This one's hard to see coming until you do it. So notice with this choice, doing my y slicing first, right? Y goes from 0 to 1. I'll let you guys think through the, which curves, what equations, solve for the, that's details. But y goes from 0 to 1. Yeah. Okay. for a given value of y, x, got to solve for x at these 2 points. That's no big deal. You get that? It's fine. Everything went fine. What if I slice the other way, though? Right? Now, it starts off seemingly easy. Okay, I'm doing my x slices first. Okay, x goes from 0 to 2. And you instinctively write down x, integral 0 to 2 dx, and you leave yourself some space in the middle, and you're all ready to go. And the problem is that for some values of x, the upper y bound is determined by a point on that curve. But then for other values of x, for these other values of x over here, the upper bound for y is going to be determined by a point on a different curve. So you're going to get totally different algebra for your y bound depending on whether x is between 0 and 1 or whether x is between 1 and 2. So which one do you write down? What do you put in this position? What do you put in that upper bound for y, for the dy integral? And the answer is you got to put two different things. It's not like you can just pick one, right? For small values of x, it is the green curve. For large values of x, it is the yellow curve. So you have to break up your integral into two separate integrals. You have when x is between 0 and 1 for that part of the curve, and then when x is between 1 and 2 for that part of the curve. And then notice your upper bound is x, as determined by that curve y equals x, for the lower values of x, and then it is 2 minus x, which is what you get on that yellow curve. Everybody see? So now, taking stock again, which do we like better? Which would you rather compute? Would you rather compute this or all of that? Seems clear choice to me. In this case, I'd rather do the top one. It's half as many integrals. Everybody see the point? So sometimes it matters which way you slice. And so again, try to arrange it to where you always leave yourself with the easy calculation to work out instead of the hard calculation to work out. Now, what's the tell here? We talked about the tell for this kind of a situation, and that is try not to invert the function. Think about what's a function of what, and then choose your differentials to be compatible with what you would like to view as a function of what. Right? So what's the tell here? The way I think about it, maybe different people think of it differently. Try not to slice through a corner. Okay, let me do it like this. I'll do this in red. The corner, I claim, is kind of the problem, because the corner is the tell that this curve that had been what we were looking at to determine our bounds intersected with that curve, right? That point that defines where the upper bound for y is, that point jumped from the green curve to the yellow curve where the curves intersected. And when curves intersect, they tend to make corners. Everybody see what I'm talking about? So try not to slice through a corner is the nice kind of geometric punchline there. And so you can see that, from that point of view, we were slicing along here, doing our dx integral, and I sliced through a corner, and thus the problem. Okay. Now, notice in this, let me go back up to the first one. I kind of technically sliced through a corner in the sense that when I started, I sliced through two corners. When I ended, I sliced through a corner. That's not a problem. Slicing through corners at the start and at the end, we don't really care, because the only thing that's important about slicing through a corner is that you have to start a new integral. Well, I was about to start a new integral here anyway. Not a problem, right? Here, before you keep going, you're going to have to start a new integral. No problem. I am not going to keep going. So it's not an issue. So of course you're going to slice through corners at the start and the beginning very often, and it doesn't matter. Okay. Alrighty. Okay, next couple of pages. This is a bunch of stuff that I have to kind of make a reference to, but this stuff is all pretty digestible, I think. It's all pretty straightforward, so I'm not going to spend a lot of time on these next 2 pages. A couple of examples of how to use a couple of properties of integrals. I think they're highly believable. This is basically the distributive rule. You think about it. Right? Don't forget what integrals are. Integrals are summations. They're Riemann sums. So integrals are summations. This says that if you're looking at a summation, and if you multiply that summation by a constant, that you can distribute that constant inside the summation. Right? It's really believable. It's, like I said, basically the distributive rule. Yeah, is everybody on board? Okay. Likewise, this says a sum of sums is a sum of sums. This is basically the associative rule of addition, kind of, sort of, not exactly, but pretty close. Highly believable, right? Sum of a bunch of smaller numbers is less than a sum of a bunch of bigger numbers. Highly believable, right? Everybody happy? Okay. Here's one that's not immediately obvious, but a double integral of 1 gives you the area of that region. Now, a lot of people will choose to view this as saying, well, if you think about the volume that you're computing there, it's like you have this area, right? And if 1 is your integrand, then you're looking at the volume of this solid whose height is 1, and that height of 1 times the area gives you the area. That's a lot of people's point of view. That was the point of view I took when I first saw this. I have an even better way to think about this. Don't forget, integrals are Riemann sums. And so let's interpret this from a Riemann sum point of view. This says if you take this domain and chop it up into little pieces and add up those areas, you get the area. Yeah? Pretty believable. So no reason to bring volume into that argument. Yeah? Is everybody happy with that? Okay, et cetera, et cetera. So I'm just going to skip the rest of these 2 pages. They're just examples of what we were just talking about, and I encourage you all to take a look, read that stuff. Okay. Now we're going to do some kind of geometric applications of integrals. The volume between 2 graphs. Now here's an example. Suppose I want to compute the volume between, this surface, that's the graph of some function g, and this surface, that's the graph of some function f. I want to compute that volume between those 2 surfaces. Now, here's a way you could do it, and there's nothing really wrong with this, but I have a preference to not think about it this way. You could think about it as, well, let's compute that volume and then subtract that volume. Right? If you take the purple volume minus the green volume, you would indeed get this yellow volume. That's acceptable in the sense of if your goal here is to actually answer the question, then that's fine, right? But I have a different goal here, and that is I want us to get some practice developing Riemann sums. Right? So let's take this as an exercise in how would I use a Riemann sum to directly address this geometry problem without reducing it to a previously solved problem. Not that there's anything wrong with that, but I just want to do something different here. So here's the idea. If I have a, in fact, let me zoom in 1 notch here. There we go. Have a better picture to look at. If I were to take this domain and slice it up in the usual way, right? A bunch of little pieces that look like this. Right. So can I think of the question that I'm interested in as being something that adds up over all these little pieces? What is it that I would add up to get the total volume, and how would I associate those things to each of these individual pieces? So I propose that what I associate to this little piece, right, is the amount of height, the amount of volume of the volume that I'm interested in that's actually sitting above that little piece. Now, it doesn't touch that little piece, but that's okay, right? We're just talking about a summation, and if I take for each one of these little pieces, for each little piece, if I look at the corresponding volume, and if I add up all the volumes of all those little French fries, then I will get the total volume of the original potato. Yeah? Everybody happy? Okay. So it always tends to kind of freak students out a little bit when all of a sudden, but it doesn't touch the thing, and it's like, well, yeah, but sure, it's just a summation. You're just adding things up, and if I add up these volumes, it gives me the total volume. Okay. Now, how do I compute that volume? Well, let's talk about this height. That's easy. It's the z-coordinate minus the z-coordinate at the top minus the z-coordinate at the bottom. We're looking at graphs. So the z-coordinates are values of functions. So it's the function whose graph is at the top minus the function whose graph is at the bottom. Okay, so g minus f. That's what I multiply by area down there. Right? And all together, here we go. So height times area gives me little pieces of volume. Right, so this, I guess I'll zoom back out. This volume here is that product, height times area. Add up the volumes to get the total volume. Yeah? Okay. Alrighty. Quick example. Suppose I wanted to find this volume over here. It's the volume sitting over the unit disk and between these two surfaces, and immediate application. Notice we're looking at two graphs, two different functions. So we take the one minus the other, right? The one minus the other, and double integral. Now, there's a couple little twists we have to worry about. To find the volume. Oh gosh, I got to make sure that the heights that I'm talking about are actually positive. How do I know the heights are positive? How do I know that this curve is sitting over and doesn't sort of slip under this curve? Right? Uh-oh. Then I'd have an absolute values issue to worry about, and how do I know I don't have to deal with that? Well, a couple different ways you can do this. Keep in mind we're sitting over the unit disk, right? Unit disk means that y squared is never going to be bigger than 1. So that is, it never breaks that z equals 1 plane. And this other surface over here, well, again, x squared is never bigger than 1. So this is actually never below 2. So one surface is always above z equals 2. The other surface is always below z equals 1. Yeah. Mm-hmm.
If we have to find the volume of curves that overlap.
Yeah, then you got to break. It's annoying. You're going to have to put absolute values in the bounds or in the integrand, right? Which means you're going to have to break up the domain into, well, where is the integrand positive and where is the integrand negative? Treat the absolute values appropriately in each of those two domains. And so, yeah, it's a little bit annoying. Yeah, we're not going to worry about that kind of thing. So that's not something we're going to focus on. But anyway, that's how you would do it. Yeah. Okay, here's a different and arguably more direct way to see what we want. I just look at this difference and observe that over the unit disk, where x squared plus y squared is never bigger than 1, this whole expression here is never smaller than 2. So it's definitely not negative. Right, this is an immediate observation. Is everybody happy? Okay. All right. So this wacky shaped volume that I want to compute there can be expressed with this integral. Now I kind of glossed over the how do we turn the double integral into an iterated integral. It's just the usual slicing process. So we have x going from -1 to 1, right, as we slice in the x direction. Yeah? And then for a given value of x, the bounds for y are going to be determined by these points. Solve for y. Specifically, solve for y on this curve. That curve, of course, is the unit diff, or the unit, well, it's the unit circle, and x squared plus y squared is equal to 1, and go through and solve for y, and you get that. Make sure you can fill in those blanks. As you'll notice, I'm starting to go a lot faster with those processes there. Everybody happy with that? You may be eyeing up this integral and saying, oh my gosh, it looks like a nightmare of an integral. Doesn't that look like a nightmare of an integral? Can you try to think in advance, how is this integral going to work out? Well, we're going to have, when we do this dy integral, we're going to have constant times y into which we're going to plug square roots. So we're going to have a bunch of square roots in our outside integral. And then, arguably worse, we're going to have a y cubed into which we're going to plug a bunch of square roots. Right? So, anyway, there's going to be trig substitutions and stuff. Y'all remember trig substitutions? Been a while? Okay, I'm a big believer in trig substitutions. I think everyone should be good at trig substitutions. Substitutions in general, of course. But let me tell you why I think trig substitutions are important, especially for those of you who are engineers, which I believe is most of you. The world is full of circles. Right? It just is. The world's full of circles, and circles are where trig comes from. That's what happened here, right? It's because this was a circle. That's why we got this expression, which gave us a trig substitution. So that's not rare. It happens all the time. It's a big deal. So if you're not super good at trig substitutions, come to office hours. Let's talk about it. I'll show you how to do trig substitutions effectively. Okay. Here's a variation on this kind of question. Find the volume between these two surfaces. Now you'll notice the way this question is phrased, it doesn't specifically say over what region. I just want to find the volume. I mean, these two surfaces cut off and define, right? They bound a single volume. Let's compute that volume. Well, that's the volume between two surfaces, and that's nice and all, but I need to know that's volume between two surfaces sitting over what domain? I've got to figure out what that domain is. Anybody see the problem? Okay, so here's the strategy. I guess that won't fit. Okay, fine, no worries. So I am looking for points such as this one. That's in my domain that I'm interested in. Notice that point there's two corresponding values of z. One is a value of one is a value of z that comes from that surface that has that equation, and the other one is this point comes from a value of z on this surface that has that equation. Yeah? Everybody happy? So what I want to know is where are the points that are on the boundary of my region? So points on the boundary here are going to be where those two z coordinates intersect, or those two z coordinates are the same. I'm looking for where the green surface and the blue surface intersect. Right? Now here's where a lot of students mess up. Lots of students, very common mistake. I see this all the time. Is students say, okay, well, if I want the surfaces to intersect, then I'll set the equations equal to each other. And the students will do like this, and then algebraic insanity ensues. Because I don't know what that means. What does it mean to set two equations equal to each other? An equation says one value is equal to another value. Right? Yeah? Here's another way to complain about this. Suppose that I were to take this equation, a perfectly acceptable equation for that plane, and just rewrite it as minus 7 equals 0. And I didn't really do anything there, but if I now set these two equations equal to each other. Well, now instead of setting x squared plus y squared equal to 7, now I'm setting x squared plus y squared equal to 0. That's different. This does not make any sense, is the point. Right? So don't set equations equal to each other. I don't know what that means. What you have to do is look at the question and ask yourself, what are you really interested in? Right? What we're really interested in here is, I want to know, when does this happen? When do these two z coordinates equal to each other? That's what you want. When does the green value of z equal to the blue value of z? So don't set the equations equal to each other. Set these two z's equal to each other. Everybody on board? So set the one z equal to the other z, and notice you've got to solve for those z's. The green z is easy to solve for because it's already been solved for. Right? The blue z, yeah, you got to, do a little bit of work there. Not a lot, but just make sure to solve for that z. That's what you set equal to each other. Everybody on board? Okay. So, having done that, you set those, whatever. Set those two z's equal to each other, and you get this equation, which algebra gives you the equation of a circle. And that's your domain. And then everything else is kind of like the previous question. Okay. All right. Okay, so I want to talk about symmetry a little bit. I've only got a few minutes left, but we're going to be able to get at least a page into this because this is a quick intro anyway. Y'all have seen a theorem from single variable calculus, right? And there's two requirements on this theorem. We need for the domain to be what I'm going to call a symmetric domain. In other words, from negative a to a, it's got to kind of flip nicely. Rorschach test and all that across over the origin. Excuse me. And the other requirement is that the integrand has to be an odd function. So if this circumstance comes up where you have an odd function and you're integrating over a symmetric domain, then the theorem says the integral is 0. No integration required. No antiderivatives. No integration by parts. Whatever. Right? And the argument, it's a pretty straightforward argument, because the curve, because the integrand, if I can draw, the oddness of the integrand, right, combined with the symmetry of the domain makes this picture where, well, look, it's just, we've got whatever positive area, if you want to think of integrals as area, right? Whatever positive we have, there's corresponding negative on the other side. Everything cancels. Right? Riemann sum, likewise. Right? So all the terms in this Riemann sum, so that term and that term, those two terms in this Riemann sum just cancel each other. Okay. All right. So turns out you can do the same thing for double integrals. This is a really, really nice computational tool. Now, in order to be able to make sense out of this, I do have to make some definitions. We have to talk about what do we mean by symmetric and what do we mean by an odd function, and they're all based on this idea of a reflection. So reflection is exactly what you think it is. That picture, X and its reflection, make a line segment that's perpendicularly bisected by the line you're reflecting over, if you want to, be precise about it. But it's exactly what you think it is. Right? So with that idea in mind, here's what it means for a function to have odd symmetry. I want, at the point X, at the point reflection of X, I need for the function to have opposite values. It's really totally like the single variable version. Right? So this is called a function having odd symmetry over the line L. Okay. Analogously, we can talk about what it means for a domain to be symmetric. The domain is symmetric if it satisfies this condition that whenever you have a point in the domain, that its reflection is also in the domain, and that's just another kind of a Rorschach, right? Think about if you're folding, over a line on a piece of paper. If you have a point that's in, well, when you fold it over, look at the reflection, that's in as well. It's going to make a symmetric domain. So very similar idea. And nice punchline. If you have a function that has odd symmetry, that is your integrand, if you have a domain that's symmetric over that same line, right, then the integral is equal to 0. Very powerful theorem. We'll talk about why next time. I'll pick up here. All right, see y'all later. Have a good Monday.